Start. So welcome everyone. We have a seminar by Hayden and he will speak about Cosmological Bootstrap.
Right. Thank you for the invitation and the opportunity to present the work. So the talk is going to be about correlation functions in cosmology and how to prove the physics of inflation using these observables. So in the coming decades, we expect to gain much more observational data that would put strong constraints on this type of primordial correlation function in cosmology. So that makes us also important for us as theorists to get a better theoretical handle on these observables at the same time. So actually, it turns out that, as I'll say more about in the talk, our present understanding of the analytic structure of this correlation function in cosmology is quite premature compared to, for example, the knowledge that we have for scalar temperatures. So, for instance, we don't even have a complete theoretical control of these correlation functions, even in tree level in cosmology. So, this kind of has motivated us to study these objects in more detail. So, in this talk, I'll try to describe a recent theoretical development towards try to understand and systematically computing this correlation function in cosmology. So based on the work we did with Nima Ben-Hamed, Daniel Bauman, and Keith Mantel. Okay, so let me actually begin with some broad introduction to the subject and try to further motivate why we might be interested in this type of observable in cosmology. So let me begin by mentioning the obvious difference between particle physics and cosmology, which is that in cosmology we don't get to control the initial states of the problem, so we only get to observe the final state of the universe that we observe today. But fortunately, the structures in the universe are correlated, not random. So this means that by studying the shape of these correlation functions of cosmological structures at late times, we can try to infer the physics that govern the earlier history of the universe. Okay? So this is like doing something like integrating in the past history of the universe in order to explain the features of the observable universe that we see today. Okay? So observationally, we have measured, of course, various two-point functions in the actual universe. So, for example, we have measured the two-point function of density perturbations, as well as the power spectrum of temperature and isotropies in the CMB. And of course, there's consistency between these shapes of these two-point functions at two different times, which has shown a mixed match between theory and observations. So, according to the standard model of cosmology, the initial conditions for these late-time two-point functions is described by a simple nearly scale invariant power spectrum of curvature perturbation, primordial curvature perturbation zeta. So here
is zeta the scalar part of the graviton? Or
right. So this is the scalar part of the
combination.
So this quantity zeta that I have here is the quantity that is conserved outside the horizon. So it will be the scalar part of the natural perturbation.
Okay.
So it's a linear combination of the Newtonian that would be conserved. Yeah, so the initial condition is described by this simple looking power spectrum of curvature perturbations. So of course, the properties of this power spectrum agree very nicely with the expectations that we have from inflation cosmology. So here, the scale invariance is fixed by the symmetries of the de Sitter background during inflation, and we also have a small tilt of the spectrum generated by a small deviation from an actual inflated spacetime from pure de Sitter space. Okay? So this slope is controlled by a small slope parameter during inflation. Okay? So the precision to which we have measured these two-point correlations is quite impressive. But actually, there's very little dynamical information of inflation contained in these two-point functions because they are pretty much fixed by symmetries of the cosmological background, doesn't contain any dynamic information. So in order to learn more details about inflation dynamics, we need to go and measure these Harvey-point correlation functions. Okay. So for instance, if you can have some self-interactions of the inflation perturbations during inflation, or you can have some extra particles during inflation that couples the inflaton in a particular way. They will decay into this lighter inflaton fuse and form these non-trivial patterns in the higher point functions. Okay. So
what's the time in this diagram?
So yeah, so this is kind of the future direction. The time goes up in this diagram during inflation. So we are computing this correlation function at some late time spatial size.
How late?
So we are computing the correlation functions once these modes have crossed the horizon during inflation. So sufficiently, some sufficient time after all the modes have crossed the horizon, so that all these curvature progressions become constant. So sufficiently late time.
This size of the cosmological horizon you're talking about is before the reheating.
Before the reheating, yes. So the size of the horizon will be constant during inflation. The physical size of the horizon will be fixed by just the Hubble constant.
So energy-wise, what's the energy scale roughly? I mean, for this, what's the size of the cosmological horizon?
Yeah. So of course we don't know precisely the energy scale of inflation. Roughly speaking, we expect it to be order the 10 to the 14 GeV scale for high scale inflation. So for example, if you measure the primordial V modes in the next couple of decades, within the sensitivity, if you measure any primordial V modes, you would point to this kind of energy scale of inflation. So the magnitude of the, for example, V mode is not very sensitive to the energy scale of inflation.
It is?
It's not very sensitive.
It's not.
So roughly speaking, it will be this kind of energy scale. So the motivation for kind of studying these correlation functions will be twofold. So first is more phenomenological, that by measuring this correlation function, we want to establish the particle content during inflation, as well as the interactions amongst them. Okay. So of course, as I said, this provides an opportunity to probe physics up to the energy scale of inflation, which could be as high as 10 to 14 GeV. And at this very high energy scale, we can imagine also spectral particles from UV physics that are out there and are produced by the cosmological background. So we want to look at these signatures of these actual particles in cosmological correlation functions. So that's the first motivation, and the second motivation will be more theoretical. That so as we have learned from many different examples, especially in the context of scattering amplitudes, it's sometimes useful to think more conceptually about the structure of these observables, to learn about the deeper structure of the theory. So we'd also like to try to ask the similar questions that we ask for scattering amplitudes, that is whether there are any consistency conditions that this correlation function needs to satisfy, and whether there's a more efficient way of computing this correlation function from a symmetry perspective and so on. So that would be the second motivation. Okay, so with that motivation in our mind, so here's the outline for the rest of the talk. So in the first part, I'll try to introduce the concept of so-called cosmological physics, which is about try to look at the signatures of actual particle during inflation and the shape of correlation functions. Okay? And then I'll move on to describe this new approach to computing correlation function during inflation, so which are split into two parts. So first I'll try to discuss in detail the structure and the derivation of the full-point function in exact Scalar space first. Okay? And then I'll try to show you how to perturb the solution for exact Scalar space to obtain the treatment function in inflation. Okay? And then I'll end with a brief summary and future directions.
By inflationary, you mean FRW solution?
Near the zeta. So
near the
yeah,
zeta,
so almost the zeta, but yeah. So we want to kind of perturb slightly the solution that we have for the exact zeta to obtain. So let me begin. So in the last 5 years or so, there has been a lot of activity trying to make this analogy between ordinary scattering in particle colliders and also the measurement of this non-Gaussian correlation function in cosmology as precisely as possible. So this program has been called Cosmological Collider Physics since the paper of Akanyama and Madasena in 2015. So just to compare the two sides of this diagram, so in particle colliders, we collide various particles and then which produces these jets that come out of these collisions. And in order to detect new particles that are produced within this scattering process, we need to measure, we need to look for resonances in the scattering cross sections of the decay products of this scattering. So that's what we do in usual particle colliders. In cosmology, we instead measure correlation functions, non-Gaussian correlation functions of cosmological structures that have been formed at that times. And to try to look for new physics or new particles during the early universe, we have to decode this correlation function and look for some special patterns that encode the presence of these actual particles in the universe. So the basic goal of this program would be to gain a precise understanding of the signatures of these extra particles on the shape of these correlates.
It sounds like almost like utopia. Isn't that forbiddingly difficult task you just said? Because in LHC physics you can measure precisely momentum, spin, charge, everything. Here we are talking about the mess. The galaxies are macroscopic objects. How can I really make a comparison?
Yeah, so sure. So, but people are actually trying to measure this non-Gaussian correlation function of galaxies and the CMB temperature fluctuation as precise as possible to learn about this. So, of course, if you go to the galaxy scale, then of course you generate non-Gaussian purely due to the gravitational evolution of these galaxies and massive structures. So really try to understand this information about the early universe will be very difficult, of course, because we have to understand the non-linear dynamics of gravity and times and so on. But once we do that, then it should be possible in principle to learn about this physics.
But for now, it's probably just CMB data.
Yeah, so far we just get the CMB data. So we have some constraints on the 3-point function and the 4-point function from the CMB.
Okay.
We haven't measured anything yet, but we hope that future larger structure observation will provide stronger constraints of these non-Gaussian correlates. Okay. So it turns out that the idea is to try to look for the signature of these particles in during inflation on the shape of correlation function, and it turns out that the signatures become most pronounced when we take a special limit of the correlation function called the squeeze limit, or sometimes it's called the collapse limit in the case of 4-point function. So the idea is that you take the momentum of the internal particle to be small compared to the overall external momentum. Okay? So in position space, this will be like taking the OP limit, where we're separating the distance between these two points to be very large compared to the distance between these two points. This is the analog of the OP limit in momentum space. So when we take this limit, that ki, the intermediate k, to be 0, then the 4-point function expression simplifies into this form, okay, schematically. So there are various factors that come into play here. So let me try to explain what each of these means. So first of all, we see that this 4-point function has an overall suppression factor that goes as e to the minus pi mu. So over here, this mu is just a parameter defined in this way, which is roughly speaking just a mass in couple units. So we see that this mu becomes real for masses greater than this 3/2 bubble, and just becomes a ratio of m over h for very large masses. So you can think of this mu as just a ratio of m over h. And this exponential suppression you can recognize as being the Boltzmann factor for spontaneously producing these particles in a time-dependent de Sitter background. So if you substitute m over h here, you can really identify this as being the m over the temperature Hubble. So you can think of de Sitter space as kind of the thermal bath having temperature that is fixed by the Hubble scale. So this is precisely the Boltzmann factor for producing these particles.
So then left-hand side, how should I think of the time, like time going?
Yeah, so time goes up in this direction, and then we are computing this kind of correlators at a fixed time, which is some sufficient late time during it. So there's some bulk process, there's some scattering process going on inside, and then this massive particle kind of decays into this inflaton perturbations, and then we're computing this.
And you're assuming that the only particles that can contribute to this is just gravity and inflaton. That's it.
So
right.
In the end, the external particles we assume it to be either inflaton perturbations or electrons.
But what about the exchange particle?
But the exchange particle can be anything in principle. I mean, in the minimum model, we also expect the internal particles to be just the interaction between inflaton and gravitons. So this external particles,
But this form of the result, is it assuming anything about the internal particle?
So this is assuming that the internal particle is some massive particle other than the...
But one massive particle?
Yeah, one massive particle. So we are looking at this 3-level diagram one at a time.
I see.
Why is it just K1 and K3?
Oh, so in this limit, K1 roughly becomes equal to the K2, because this Ki is really the sum, the magnitude of the sum over K1 and K2. So Ki going to zero limit is really K1. Yeah.
Do you impose some boundary conditions in the past, or do you have any sources?
Right. So usually we assume that the initial state of this is described by the standard vacuum in the past. So if you go to a sufficiently earlier time, then you're going to superpolarize and scale. So in that case, we don't expect the modes to feel any effects of curvatures. So in that case, we expect the initial conditions of this was described by the standard vacuum in that case. So that's called the bunch Davis initial states. So this calculation is assuming that the initial state is given by the standard vacuum in class case. Any other questions?
So mu, like what does like mu being imaginary or like on real?
Right. So yeah. So for very small mass, then this mu can become imaginary. In which case, this kind of oscillating factors, the imaginary powers, become real. So here we have two contributions, one of which is plus mu and the other of which is minus mu. So actually one of these dominates when this mu becomes imaginary. So only one of the terms survive. And in that case, this would have just a smooth scaling behavior if we take a squeeze limit. But here, when the mass is large, so that mu becomes real, this has this imaginary component, so that the Fourier function becomes oscillatory for massive particle change.
And that massive particle, do you take it to be a scalar massive particle, or is it?
Yeah, so this expression is for scalar, but if you have some non-zero spin internal particle, then you also expect to have some angular dependence as well, which I can show here.
And spin dependence, right?
Spin dependence, yeah. Yeah, essentially
Any
it's just
spin, including higher spin.
including higher spin.
Okay.
Yeah. So yeah, essentially it's just given by some Legendre polynomial of the degree x by spin of the particle. But yeah, so this expression is for the scalar. Okay. Yeah, so as I said, for large masses, this Fourier function shows this oscillatory behavior, whose period just becomes precisely fixed by this parameter mu. Okay? And also there could be angular dependence if you're exchanging a spinning particle. So the bottom line is that by measuring this shape of Fourier function in the squeeze limit, you can extract both the mass and spin of the particle by looking at the shape dependence. Also, you can compute the phase of these oscillations, which is also a function of the parameter mu. However, there's also a slightly small downside to this expression, which is the dilution factor that I showed you here. So basically, if you take Ki to 0, there's a dilution factor that goes at Ki to the cubic power, right? So this is nothing other than actually just the volume dilution that goes as 1 over the three-dimensional volume with the expansion of the space-time. So actually, although this kind of signature of this extra particle becomes the cleanest, becomes most transparent when you take a squeeze limit, in practice it might be a little bit difficult to detect this effect because of this dilution factor. So this kind of motivates us to know whether we can also look for this extra this signature of extra particles beyond just the squeeze limit, where the signal might not be suppressed by this volume dilution factor. So this motivates us to kind of study this the shape of the full point function beyond the squeeze limit. Okay. So the standard way of computing this correlation function in cosmology is by computing Feynman diagrams using the so-called Inning formalism or the string-on-Cavendish formalism, which is a formalism appropriate for computing correlation function in a time-dependent setting. So if you try to compute this Feynman diagram, you basically end up with this kind of integral form. So in cosmology, we don't have time transcendental symmetry, of course. So we only Fourier transform in the three-dimensional spatial coordinates, and then we are left with this explicit time integrals to do at the end of the calculation. So even at tree level, we have to do this integrals for cosmological correlation calculations. So we have this time integrals for each of the interaction vertices here. And the integrand consists of this multi-boundary propagator for this external legs. So in the case where these external fields are massless, then this multi-boundary propagator actually simplifies into this exponential form, simple exponential form. Okay? So this is some simple form for massless particles. But there's also this bulk propagator that corresponds to this propagator for general massive particles. That actually can be written in terms of some Hankel functions. Okay? So the brute force calculation of this Feynman diagram would lead to this type of double integral. And there's also some time modelings inside this propagator. So this makes it very difficult to compute this integral directly. And people have only been able to compute this integral numerically so far. So really, just computing this tree-level correlation function in cosmology is really the frontier in relational correlation theory on the force scattering.
How is the computation in the ASCT? So maybe you can do just some analytic continuation from the computation in AES, whereas in principle it's known the way it is.
Yeah, so in principle, yeah, if you I think most of the AES calculations have been traditionally done in position space or in matter space. So in principle, you can try to Fourier transform those results to momentum space. But I think in general, it's very difficult to directly Fourier transform those results to momentum space. So I think most of the calculations in cosmology so far have been directly done in momentum
But
space.
how can that be
But
essential issue? I mean, I can work in either space, right?
Yeah,
So
sure.
when you say that it is not known or it hasn't been computed, surely one should give allowance, right? To
Yeah, so yeah, it has been computed in the, yeah.
So has it been computed in space rather than in position space rather than momentum space?
Yeah, for example, just a 4-point function of scalar fields with the scalar exchange have been computed a long time ago in ADS space, in position space.
In ADS, yes, but here?
Here, I don't think any result has been translated into momentum space.
But didn't you just say a moment ago this is the Sitter calculation?
This is this sort of calculation.
But then the Sitter and anti-de Sitter are technically extremely close, aren't
Yeah,
they?
they are similar, yeah. So if you can compute this in ADS space, the sort of calculation just related to by analytic configuration.
And yet it's not done.
It's not done in this Fourier space.
And why do you prefer Fourier space?
Right?
Why do you prefer Fourier space?
Also, because all the data analysis in cosmology is actually done in Fourier space. Yeah, because in linear perturbation theory, the scalar vector and tensor decouple in Fourier space. So I think traditionally people do calculations, cosmological calculations, always in momentum space. Yeah. So we were kind of motivated to compute this full 4-point function, and so in the rest of the talk I will try to explain how a symmetry-based and non-Lagrange way of computing this diagram without using Feynman diagrams can help obtain an analytic solution to this relation. Okay, so let me now come to the method. So first of all, what do we mean by bootstrap? So the traditional way of computing observables in quantum theory is, of course, by computing Feynman diagrams. So to do that, we first start with some physical principles, such as the symmetry of the problem and other physical constraints, such as unitarity and Lorentz invariance. And then we write down the Lagrangian for a particular theory, we solve it for the motion, and then finally compute the Feynman diagrams to get to the observables. And in between, we might have to deal with some offshore redundancies for massless scaling fields. However, as we have learned from many different examples, especially in the context of scalar amplitudes, this more than often obscures the simplicity of the final answer. So for the purpose of computing these observables directly, it's much more efficient to directly start from the physical principles and then try to exploit the structure to determine these observables directly by passing these intermediate steps. Okay. So of course, this has been the heart of the modern scaling amplitude program as well as the component bootstrap. So we like to use a similar logic to compute this correlation cosmetic components. So let me begin by actually reviewing how the structure of the whole particle amplitude is fixed by symmetries and singularities. Okay. So first of all, we have Lorentz invariance. So that makes us possible to express this whole particle amplitude in terms of just the Lorentz invariance, invariance SMT. At low energies, this amplitude just becomes an analytic function in terms of these Mendelssohn variables. So that means that at very low energies for small SMT, we can basically expand this into a power series in terms of these SMT variables. But as we go to higher energies,
but Lorentz invariance is not enough to make this statement, right? I mean, you need more. What else do you use? I can have some other strange functions of SMT.
Right. So another assumption that goes into the so I think the assumption is the only type of non-analyticity of the scaling amplitudes is given from this physical production of extra particles. And there's an assumption that goes into the non-analytic structure of these extra particles. For example, at tree level, we only expect to have this kind of simple poles at the location of the particle's mass. And if you go to loops, and you can have some branch cuts and so on. But the assumption is that the only type of non-analyticity is produced from this physical production of extra particles. If you don't have any extra particle production, then amplitude should be analytic.
It's kind of locality.
Locality, yeah, causality argument, yeah. Yeah, if the theory is causal in real space, then if you go to Fourier space, then it should be analytic in certain domain of the function. So that's the assumption. So I think people have proven this statement productively, but not non-productively. So here you kind of want to put them closer. So yeah, so as you go to higher energies, we become sensitive to the exchange of this heavy particle, and we expect to have a simple pole at the location of this particle. And if we go to this pole, then by unitarity, we expect the amplitude to be factorized in terms of product of three particle amplitudes. And if we sum over all the intermediate hedicities, then we expect to that should give rise to a specific angular dependence that's given by this angular Legendre polynomial with the degree given by the spin of the particle. So yeah, so this full particle amplitude of massive scalars that are shown here are actually very easy to compute by hand. But I should emphasize that no Feynman diagram or Lagrange description is actually needed in order to derive these results. And of course, this is very useful way of computing scaling amplitude when you consider spinning particles. So this way of kind of non-Lagrangian symmetry-based way of thinking of the problem can help computing this scaling amplitude more efficiently. So then this cosmological bootstrap would be just a similar systematic way of computing these correlated functions using symmetries and singularities. So in particular, we'd like to compute these correlations in a way that parallels kind of the modern way of computing scaling amplitudes. Okay? So the basic idea is that we have these boundary correlation functions during inflation, and we are computing this correlation at certain spatial boundary in some time in the future. So the approximate isometry of this space translates into weakly broken conformal symmetry for this boundary correlation functions. And since the number of generators of four-dimensional De Sitter space is actually equal to the number of isometries of one curve group, we can also express this four-point function in terms of just two independent variables which are labeled as U and V. So the idea is that by imposing this conformal symmetry, we expect the four-point function to be invariant under the action of conformal generators. Okay? So this Ks will be the generators of conformal group, and the action of this, which will be some differential operators, and the action of this differential operators on acting on F should be 0 for this four-point function to be invariant under conformal transformations. So the strategy would be to, instead of computing time intervals using Feynman diagrams, we instead solve this differential equation. Of course, this differential equation contains less information than the explicit time intervals because, for example, it doesn't know anything about the mass of the intermediate particle. So we have to, in order for this solution to correspond to some physical process in the bulk, we have to supply some physical boundary conditions in order to fix the solution. So I'll also explain how we could do that. So that's the basic strategy. So let me now begin by, first of all, reviewing some basic kinematics and symmetry of the problem. Okay. So first of all, the decimal isometry also contains spatial isometries. Okay. So these are spatial translations and rotations. So first of all, spatial homogeneity gives rise to this momentum conserving delta function for spatial momenta. And in combination of spatial isotropy, you can write the 4-point function in terms of these 6 variables. The magnitudes of the 4 momentum plus the variables that are labeled as S and T, similar to the Mendelssohn variables. So here, so due to the momentum conservation, the 4 momentum needs to form a closed shape like this. And this K1 to K4 is just the length of this shape, 4-point function. And S and T is just labeled the length of the diagonal axis of this.
Why is there no energy conservation?
There's no energy conservation in cosmology because, of course, there's no time-transient symmetry. Yeah. So we don't have the full Coulomb-Kerr symmetry. We just have a spatial symmetry plus the extra symmetries that I'm going to talk about. So the extra symmetries would be, one of which will be scaling symmetry. Okay, so scaling symmetry basically means that when you scale this momenta appropriately, then this 4-point function will have a corresponding scale. So basically, it says that the 4-point function is some homogeneous function with some degree fixed by the dimensions of these fields. So in order to make this manifest, it's more convenient to use some dimensionless variable and in fact try particular scaling out of the problem. So I'm just going to define these UMV variables, which are some dimensionless variables defined in this way. So I'm just taking the ratio of this diagonal vector S and the sum of the each of the 4-point function and vice versa for the V variable. Okay. So these are some useful definitions. And I'm also going to define this dimensionless version of the 4-point function F hat, which are defined by factoring out some pseudo powers of this S variable. So this powers in S would be fixed in terms of the mass of these fields that appear in the 4-point function. So symmetry constraints so far have been rather trivial, but really the non-trivial constraints comes from imposing conformal symmetries. More precisely, we require the 4-point function to be invariant under the so-called spatial conformal transformations. Okay. So this second order differential operator in momentum is really just the generator of this spatial conformal transformation. Okay. And the sum over all of these generators from 1 to 4, acting on F should be clear.
So these are conformal boost generators?
Yes.
Yeah. Now, what makes this near the sitter, by the way? You said near the sitter.
So here, everything is purely sitter. Okay? So I'm not. So here, so this 4-point function should vanish in the exact sitter space, but there will be some small term left over when we go to.
So the sentence about the box, you don't need the word near.
Yeah. So here we really don't need the word near.
Okay.
But so I just put the word near because eventually we're going to be solving this equation for the point vector.
Okay.
Yeah, but this equation is for the choice there. Okay. So just to explain some notations, so here delta is the so-called scaling dimension of the phi field, okay, which is just a function of the mass defined in this way. So for example, if you take phi to be massless, then delta becomes 3. So the idea is to solve this differential equation, and we decided to work in terms of the dimensionless variables that are introduced, the UMV variables. So we can do some change of variables to recast the conformal constraint in terms of these variables, and it turns out that in terms of this UMV, the conformal constraint can be written in this convex form like this, okay? Where this delta U and delta V are some second order differential operators. Defined in this kind of hypergeometric form. So So actually, this equation is only true for fields that have this particular mass in our units, which has this conformal dimension of 2. Okay. So this corresponds to computing 4-point function of instead of massless scalars. Instead, this equation applies for 4-point function of conformally coupled scalar fields, which have this particular mass units. So we're first going to solve this equation for this particular case, because it turns out that the equation is simpler, but eventually we will also look at the actual solution of massless 4-point function. Okay, so what this equation really means physically is that it tells us the behavior of the 4-point function as we scale these 2 different variables. So for example, the evolution in the u variable will tell us how the 4-point function behaves as we kind of stretch the 2 sides of the 4-point function while leaving the other 2 sides fixed, and vice versa for the v variable. So that's basically what this equation means. So here, of course, we haven't assumed anything about the actual process in the bulk. So what we have to do, so that the basic goal of this would be to try to solve this differential equation, but first try to classify the solution according to their analytic structures, which will satisfy some different equations. Okay? So first, we're gonna start with by looking at the contact diagrams, which turn out to have the simplest possible analytic structure. And then we're gonna be looking at the tree exchange 4-point function, which have a much richer analytic structure and captures the effect of particle production. And finally, there's a particular limit that you can take to obtain the infinite tree function. So we'll be looking at this one by one. So I mentioned that the contact diagrams carry the simplest possible analytic structure. So what exactly is this? So it turns out that the contact diagrams can be simply classified in terms of the inverse powers of this total energy variable E. So E is defined in this way, where it's just a sum over all the momentum. So as I just said, there's no energy conservation in cosmology. So rather than having a Dirac delta function imposing energy conservation, the total energy show up as some poles in the shape of coordinates. So it turns out that the simplest solution is actually given by simply just taking 1 over E. Okay? So this actually you can check by direct computation is the same as the 4-point function that you can compute by this bulk 5 to the 4th interaction. So you can check that the 2 sides actually agree. But having obtained this simplest solution, it's very easy to construct all the higher order contact diagrams, which you can simply obtain by acting with this delta U operator multiple times. Okay? So you can easily check that this quantity, after having applied this delta U operator multiple times, obeys the previous delta U minus delta V equation. Okay? So since this is a second order differential equation, second order differential operator, you will bring down 2 powers of energy total for each of the action of the delta U operator. So the higher order solution will have higher powers in this energy total. And then you can also check that this higher order solution actually corresponds to the 4-point function that arises from high derivative interactions.
What if in the bulk I have infinitely many terms with ever increasing number of derivatives on 4 scalars?
Right.
Can you say anything about that?
So of course we don't know about the specific coefficient of this.
Well, let's have an arbitrary.
Yeah, then it will be just written as just a series. Just a series in terms of this delta U operator with some
And that may easily diverge, right? In the energy plane in space.
So if you have an infinite number of such terms, we expect those to be kind of resummed into something else, right? So for example, if you go to low energies and then do the EFT expansion, then you might find that the answer might diverge at some particular scale, or if you consider infinite number of terms, but then you know that the final answer is finite. So actually, that's actually what we're going to do. Rather than summing over the infinite number of contact terms, we're going to actually be solving the full theory with the exchange of extra particles. So that kind of captures the effect of.
Are the higher derivative couplings suppressed by any mass?
Right, so there should be some suppression in the mass scale, which I haven't shown here. Yeah, each of these higher dimension contactor will be suppressed by 1 over m squared for each of the So yeah, so this would be suppressed by 1 over m squared, and this would be suppressed by 1 over.
And that m, how is it related to ADS radius? The city radius, sorry.
So this suppression m scale would be related to the mass of the particle that you have integrated out rather than the Hubble scale. Right? So if you start with some UV theory with a heavy particle and then you integrate out the massive particle, then low energy
So
radius.
that mass is up to me. It's not dictated by the city radius.
It's not dictated by this area. Right. But we expect the suppression scale to be higher than the Hubble scale because otherwise we don't integrate it out.
I see.
So I think already at this level we can see that this way of computing correlation function is very useful because you can obtain all the higher order contact solutions in this particular simple way. But let's now move on to the more interesting trade-level exchange diagrams. Okay. So it turns out that the previous conformal constraint that we saw actually can be decoupled into a pair of ODEs, ordinary differential equation, in terms of U and V variables separately. Okay? So this is the equation, for example, in terms of the U variables. So we say that this equation has a structure in such that the contact diagrams we have just classified act as a source term for the trade exchange diagram. And this has a particularly simple explanation. So imagine that you start with some UV theory with the heavy particle, and then you integrate out the massive particle. Then you expect the low energy theory to be just destructive in terms of the contact term. And this is what precisely happens when you take the large mass limit of this equation. Then you can simply drop this operator, and that just becomes proportional to the contact term. So this is roughly the structure of the equation. So this operator acts like an operator that collapses the the internal propagator, so that the right hand side is just described as a sum over the contact terms that we have specified. Okay. Actually, it's kind of interesting to see that this structure is completely analogous to the structure that we have for scattering amplitudes, where by multiplying by this inverse propagator for the exchange particle for this three exchange open function, the right hand side should be completely analytic function in terms of the Anderson variables, which correspond to the power of contact terms. So the strategy would be to try to solve this differential equation. So I've now explicitly substituted the form of the delta E operator and the simplest contact term on the right hand side. Okay. So we can try to solve this equation, but it's interesting to note that similar to the scattering amplitude having this particular singularity at the location of the pole, this correlation function also has some singularities at some particular locations correspond to some physical processes. So let me mention some of them. So first of all, there's a singularity that you can reach by sending U to minus V. Actually, this is just a 1 over E in terms of the total energy. So this is like taking the total energy to be 0. Basically, so that's equivalent to importing the energy conservation, right? So by going to this particular pole where we send total energy to be 0, this is equivalent to taking the total energy conservation. So this is actually a mass taking the flat space in it. So the coefficient of this singularity we expect to reproduce the full particle activity in flat space. So this you can actually check from various examples. So that's one of the singularities, and there's another singularity from the coefficient of this operator. Okay, so there's a singularity when you send U to minus 1, and similarly for the V variable. So this is actually similar to taking the flat space limit for the whole correlation function, but rather than taking it for the whole correlation function, you take the flat space limit of each of the interacting vertices. So when you take the singularities, each of the coefficient of the singularities is actually described by the three-particle amplitude in flat space. So that's another interesting singularity. There's another singularity coming from the same coefficient, which is the singularity when you send U to plus 1. So unlike the previous singularities where you had to send the energies to be negative, this actually can be reached by physical configuration with positive energies. Okay? So this visually this corresponds to taking this domain where the 4-point function becomes just a similar to the three-point function, where two of the magnitudes, two of the momentum align each other. Actually, this is not the type of singularity that we expect to have from physical correlation function, because it's just a limit where we send the four-point function to three-point function. So actually, you can show that this type of singularity is actually absent when you assume the standard value in each condition. So, so the strategy will be to impose a certain boundary condition that removes this singularity. Okay. So we take a particular limit of the particular linear combination of the homogeneous solution to remove this singularity in the final solution. So when you do this, here's the result that we get. So for simplicity, let me just show you the solution in the small u limit. Okay. So the full solution consists of two different parts. So first of all, we have a particular solution to the inhomogeneous differential equation, and also some special linear combination of homogeneous solutions that removes this singularity. Okay. So first of all, this particular solution is actually just the usual EFT expansion. So you see that the coefficient of this series expansion is just given by 1 over mu squared for large masses, and that basically just goes as h squared over m squared. So this is the usual EFT expansion, and we also see that the EFT part of the solution is a completely analytic function of this momentum variable, just like scalar amplitude. However, the analyticity of the full solution is actually spoiled by this non-perturbative correction that goes as e to the minus n. That is the Boltzmann factor we talked about for spontaneous precision particles. We also see that the momentum dependence of this non-perturbative correction is also non-analytic because it has a lot. So there's also branch code produced due to this the physical particle production, similar to what we have for scalar amplitudes. And we see that the period of this oscillation is precisely fixed by this operator mu. Okay, so so far we've looked at the structure of the four-point function of this particular scalar field that have this particular mass over units that correspond to conformally coupled scalar fields. Okay, so let's now look at how we can obtain various other type of correlation functions starting from this object. So this will be the fundamental object that we start with, and for experimental interest, we are more interested in obtaining this four-point function of masses influenced on perturbations. Okay. Actually, remarkably, it turns out that we don't have to solve for a new equation in order to obtain this object, but actually there's something called a rate-shifting operator, which is some simple differential operator that takes the solution of conformally coupled scalars to masses scalars. So somehow conformal symmetry relates these two objects through this differential operation. So yeah, that's called the rate-shifting operator because you simply shift the kind of conformal weight or conformal dimension of the external fields. There's also something called the spin-raising operator, which is also some similar looking differential operator that takes the solution of scalar exchange to the solution of the spin exchange solution. So in this way, deriving solutions, we never have to deal with the indices of spinning fields or gauge redundancies. We simply have to act with this spin-raising operator to obtain the four-point function of arbitrary spin exchange.
When were these constructed in the literature? Spin-raising operators, are they very well known from old days, or?
So this, both of the spin-raising and rate-shifting operator we derived in this work.
Oh.
So are these like in principle similar to the weight-shifting operators in conformal theory?
Yeah, I think so. When we were deriving this rate-shifting operator, we were deriving it directly in momentum space, but they should be actually related to this other rate-shifting operator constructed in conformal theories. Yeah, so if you were to Fourier transform those operators to momentum space, those would be actually equal. Okay, so there's one. So finally, there's a particular limit that you can take from this four-point function to obtain this three-point function, which is just taking the soft limit where you take one of the external momentum to be 0, which amounts to taking this free derivative to 1 in our language. So as I described in a few slides, by taking this limit, you can derive the inflation theory. So let me be more specific and describe how we could obtain these inflationary correlation functions from this particular open function that we solved. So first of all, we will have to consider two different steps. So first of all, we have to make the external fields masses from couple and couple fields. So that is by taking the solution for delta equals 2 to get to the delta equals 3 solution. And then after that, we will have to take a particular limit of the open function to derive the three components. So this actually amounts to evaluating one of the external phi fields to be on the time-dependent background. So it will kind of bring out this phi bar outside the correlation function. And this phi bar dot can be related to the Scalar parameter epsilon. So I'll try to expand it. So first of all, to do the first step, we apply this wedge-shifting operator on the desiderate invariant open function. Okay? So we take this open function for delta equals 2 and apply this the so-called wedge-shifting operator twice on the open function, each time on the 1, 2 leg and 3, 4 leg of the open function, and that should give the open function for delta equals 3. Okay? So for example, one of the forms of the operator for scalar exchange would take this form. And the form of this wedge-shifting operator would be different for different fellows in exchange type. Okay, so once we have obtained the open function for delta equals 3, we can now take this the so-called soft limit to obtain the inverted Drupa function. So rather than applying this wedge-shifting operator twice on the F solution, you now first we have to recall that the inflaton is not exactly massive, but has a small mass, given by controlled by the Scalar parameter. So that effect can be incorporated by remembering that the scaling dimension can be related to the mass of the field. This effect of not exactly massiveness of the inflaton can be incorporated by shifting the dimension by epsilon amount. Okay? After you have done that, you take the soft limit, and it turns out that the leading effect actually vanishes. So the soft leading effect that is proportional to epsilon is the leading contribution to this.
Epsilon is constant, I suppose.
Epsilon is constant, yes. Okay. So for this, you just take one of the wedge-shifting operators and evaluate it at the equals 1 configuration. Okay, so with
That
this,
phi of t is supposed to solve Einstein equation coupled to scalar in standard cosmology, right?
yes.
But you told us you're not looking at any Lagrangian, no Einstein Lagrangian, no potential, none of that. So how do you make connection? How do I know what this phi of t really is?
Yeah, so here so everything we talk about is the correlation function of perturbations.
Mm-hmm.
So this formula knows nothing about the inflation background, for example. So it knows nothing about the inflated potential, but it simply assumes that there's some slow expansion. So this formula assumes that all the interactions are controlled by Rickley-Broker hormone symmetry. So we assume that the inflated potential has a very small slope controlled by this slower parameters, but assumes nothing more than that. So if you, for example, if you have some strongly time-dependent interactions, then this formula wouldn't apply because it breaks hormone symmetry in a stronger way than we assume. So it assumes something about the interaction structure. Okay, so in this language we can write the general inflation circle function. In terms of just the two seed functions that we solved for the delta equals 2 case. Okay. So inflationary circle function also first of all has an overall epsilon suppression, and the general solution can be constructed by summing over the spin exchange and the higher derivative order solution of the quantum interaction and the spin exchange over the function. So in this case, the structure of this triple function is completely fixed by symmetries, and model details only enter through the size of these arbitrary quantities. So finally, let me highlight visually some of the spectroscopy features of these open functions. Okay. So for example, the left panel is just a familiar plot of the production of z bosons in particle colliders. Okay. So in this case, the location of this resonance peak is fixed by the mass of the particle that has been produced. And the shape away from the peak at low energies is determined by the EFT expansion. On the right hand side is a plot of the 4-point function as a function of the momentum ratio for the U variable. And we see that when you go to this squeeze configuration, we start to see these oscillations with the period which is fixed by the mass of the particle. Okay? So this would be the exact analog of the resonance peaking in the case of colliders. So for example, if you were to Fourier transform this oscillation, it would look like a peak in real space. So this is the analog of the resonance peaking in the case of cosmology, and then the shape away from the squeeze limit is dictated by this EFT part of the solution. So I think with this picture, we now have a kind of complete dictionary of the cosmological physics, where we have a description for both of the EFT part and the particle production in a single unified framework. And we also provide some exact template for expanded searches for this non-directional correlation for oscillations. And if the intermediate particle has a non-zero spin, then you can also look at the angular dependence. So, for example, if you also go to squeeze configuration and measure the angular dependence as a function of this angle, you will see that the angular dependence precisely becomes the Legendre polynomial in this squeeze configuration. So this is how you can extract the spin of the intermediate particle. So let me now summarize. So in this work we took some initial steps of systemizing the computation of these differential correlation functions, and we saw that the space of correlation function is completely fixed in terms of these simple seed functions, which was just a 4-point function of components of the scalar fields, and there was this various rate shifting operators and spin rating operators. They take the solution to different various cases, and then we could also take the soft limit to get the throughput function in inflation. So far we've only talked about the scalar 4-point function, but of course we could also try to use the same formalism to try to complete 4-point function with spinning fields, spinning standard fields. And a particularly relevant example would be the correlation function of the graviton. So the graviton is another guaranteed degrees of freedom during inflation, apart from the gravitation. So this is a particularly relevant example. But it turns out that the graviton correlation function in inflation is hardly known beyond the trivial function. Okay? So people haven't completely computed the graviton 4-point function before. So one might try to use the same formalism to compute this object. In particular, we would like to understand whether there's also some other type of operators that kind of reduce the spin of the external fields, so that we can simply relate this object to previous kinetic solution. Of course, the story will be slightly more complicated because although the scalar 4-point function is completely fixed by symmetries, this 4-point function of external spinning fields is not completely fixed. There's some independent structures that you can have. So the story will be more complicated, but in principle, you should be able to read this in terms of this language. And in flat space in particular, we know that the full particle amplitude of graviton is very strongly coupled. So one might ask whether there are similar persistent conditions for this graviton. So this is actually work in progress. So finally, let me mention some remarkable property of these correlation functions, which is the fact that this correlation function actually contains flat space scattering amplitudes by some pseudo-dynamic configuration. So I told you that these total energies, rather than showing up as Dirac delta function, they show up as these poles in correlation function. And going to this pole is like taking the flat space limit. So we expect the residue of this pole to be equal to the flat space scattering amplitudes. And it actually turns out to be true and can be checked in many different examples, for example, in these references. So I think many of the insights into the physics of scattering amplitude must have analogs in the case of cosmological correlators. And I think it will be very interesting to further study this correlation function using this language. So thank you. I'll stop here.